I've pushed all the buttons. Now. I pushed some of them a few times because I had a bit of lag. So welcome to episode 144 of Quarkus Insights. We're going to be talking about all things GraalVM and Mandrel and Leyden, and we've got Andrew Dinn as our guest. So Andrew, do you want to introduce yourself?
Hi, yes, I am a distinguished engineer at Red Hat. I'm a member of the OpenJDK team, although strictly with the Java team, because as well as doing OpenJDK, we also do GraalVM, and I've been particularly involved in efforts to upstream code into GraalVM. But I'm also still heavily involved in the OpenJDK project, where I'm a project reviewer. And I've also obviously got drafted in to try and see if we could get something in OpenJDK that had the sort of footprint and startup performance of GraalVM, or something that was near that. So I was involved in pushing for and then eventually helping set up the Leyden project, and have been to a small degree involved in that work, although that work has been done by some of other engineers. And thankfully now Oracle have really come on board with Leyden, and things are happening there. There's a whole lot of work that they're doing as well, which I'm obviously keeping an eye on and interested in seeing developments in.
Cool.
Awesome.
And so 2 pieces of housekeeping, because we don't have any slides. So if we're going to be asking questions, but if anybody else has questions, then please do pop them into the chat. And also, before we start on the questions, Max.
Well, we released what's called Quarkus 3, a bunch of Quarkus 3.2x last week, with all the regular updates. And especially also we released the productized Quarkus, Red Hat Builder Quarkus 3.2, I forgot the number now. But that means that for a long time, we've had this want to have a long-term supported version of Quarkus. So that's now officially in play. It's called Quarkus, the Quarkus 3.2 stream, so where community and product are aligned. But the thing I actually want to inform about is that we had a CVE coming up in Gradle. So the plugin, Quarkus plugin, unfortunately had a little extra feature of recording the secrets in the environment in your build. It only happens in certain extent, so it's not like everything, but if you're using Quarkus and what's called a mutable jar, that artifact could by accident contain secrets. So that issue is fixed in Quarkus 3.2.8 and Quarkus 3.5 and I think 3.6 when it comes out. So just a heads up, go look at the release blog. There's a link to the CV, explains what it is, and it's just great. The Gradle security people made us aware of it, so that came out last week. So if you're doing Gradle builds and using mutable jars, be aware of this one and update. Mind you, this was not an issue. This was not a Quarkus 2 issue. This is only in the 3 family that this bug has seeped in. So anyway, now hopefully fixed in all the streams. So, yeah.
Hooray.
Cool. And by the way, I'm getting a weird echo or slowness on my side, so I'm not sure if my network is being bad. But if I'm making no sense, then let me know.
Yeah, and we're getting a bit of buzzing from your microphone as well for a change. So
the gremlins that always affect Max are back again.
Yeah. I mean, we're sort of here to talk about Quarkus, but we're also just here to debug Max's AV issues each week.
That's what I'm for.
We can just make fun of him now because he's on mute. So less about Max's microphone, and let's start by talking. Shall we start by talking about Mandrel, and for those who don't know what it is and why we have it?
Yeah, so that's a good place to start. So obviously we've been interested in GraalVM native as a delivery vehicle for Java applications in general and Quarkus in particular, and so. We were actually involved with GraalVM quite a way back, working on the port to make AR64 work in GraalVM for the compiler. But when the native stuff really started to get actually something that was usable, we looked at it and we thought, well, we really want to have this and be able to use this for deploying Quarkus applications. But one of the things that made that difficult is that GraalVM uses a custom build of the OpenJDK release that comes out of Oracle Labs. So it's not a standard Java release. And it's evolving at a different pace, therefore, to OpenJDK with different software in it. And then there are other issues to do with the stability and some of the functionality of GraalVM that we're all also interested in. So we thought, if we're going to be able to support Quarkus applications using GraalVM, we really have to have our own management, our own release management, and our own model for deploying and supporting applications on a more reliable and well-known base than the one that's coming out of Oracle. We need it to tie into the OpenJDK releases that we have, that we support already in our operating system, and make sure that we've got the same Java that runs the native image generator and then is built into the native image. And it's based on a release that's a known quantity that's the same as all the rest of the things we're supporting. So when we thought about in the future, not just people experimenting with GraalVM now underneath Quarkus, but actually having a supportable product, we thought we'll really need a downstream of the code that Oracle provides in GraalVM, and to base that on a standard release OpenJDK, and that's something that we can support. So Mandrel is really just a downstream product. It's actually almost completely identical with upstream GraalVM, but it's got a few tweaks to make it work on the latest Java release. And we have to maintain a version that will keep, that's currently JDK 21. We're going to maintain a version that keeps working on JDK 21, even as the GraalVM code moves forward to JDK 22, 23, and so on. Oracle actually are doing the same thing, but they're not necessarily guarantee that's available for all of their open source users, for their community users. There's a pressure for people in the community to move forward to use the community edition on more recent JDK releases, or to shift to their enterprise release. So really, Mandrel is our way of keeping control over the releases and making sure we actually have a known base that we're able to support. There's not that many changes to OpenJDK that are made in the labs releases, but we're experts in OpenJDK as it comes out of the OpenJDK project. So it's much easier for us to support OpenJDK as a normal release. And also, our customers already have OpenJDK installed. So anything we deploy on top of the existing OpenJDK is easy for them to install. Having to have them download something that comes off the Oracle site is difficult. And it's difficult for us to be sure that we've got the right bits in place, that we've got the release management and the update management that works for them. So it's really very much about housekeeping and product maintenance and product control. It's not really about divergence from what Oracle are doing, except in order to be able to have a reliable release management and control process. There is one other thing as well. GraalVM has, as well as the native image capability that's really attractive to a lot of Quarkus users, for some of our users, they're also interested in all the polyglot capability that comes out of using the Truffle interpreter framework and the various languages that have been ported to run on Truffle. And that's absolutely amazing technology. I really think very highly of the job that Oracle have done there. It's great technology, but it's not a major part of our business model at the moment to support that. So Mandrel is actually a subset of GraalVM. It's the subset that gives you native image. It doesn't bundle in Truffle and any of the Truffle languages. Obviously, our customers who are interested in using that can use the GraalVM downloads and the Oracle Labs JDK, and they can have all that capability. And we're making sure that Quarkus is compatible with all that upstream GraalVM polyglot capability. We're not making it difficult for anyone to use it. But in terms of our plans for our product support for Quarkus, we're looking at Quarkus with native image only as something we will support. So Mandrel is really the base for doing that, for having a productizable native image-based Quarkus.
Cool. And we've got our first question.
I think because I just stopped to take a breath. That was my short answer. I'll give more details later. So,
yeah.
Yeah, you go, Max.
Well, I hope my mic is working now, but if not, yeah. So this is the good fun one, like versioning and naming, right? So
Mandrel naming's hard, yeah.
Yeah. Well, Mandrel aligned with a recent GraalVM for JDK 1721 naming change as well, instead of year-based numbering. I'm not sure it was ever year-based numbering, but yeah. If you want to, I have a comment on this, but I'll let you go first, Andrew.
I think we're going to move towards describing it as Mandrel for JDK 21 and so on. But one of the problems is that we will be supporting Mandrel for JDK 21 while 22, 23, 24 are coming out, and then we'll move to Mandrel for JDK 25. We are maintaining a stable version for 21. And this change to GraalVM for 1721 is because when GraalVM GraalVM is slowly being merged into OpenJDK, and each change that's made to GraalVM will be made in a new OpenJDK release, 22, 23, and so on. And at the moment, there are no OpenJDK backports that include the full GraalVM. So there isn't a maintenance model for maintaining GraalVM in LTS releases at the moment. Even with 21, we have to go into that situation because we don't actually have all of GraalVM in OpenJDK. We just have the JIT compiler and a few of the libraries. We still don't have the native image generator or any of the polyglot code yet merged into OpenJDK. So the thing that is driving this naming change is that when you release OpenJDK 22, you get GraalVM 22 because it's part of OpenJDK 22, and the same with 23 and so on. Unfortunately, there's still a lot of GraalVM that's outside, so Oracle want to tie the external code to the OpenJDK releases with this naming convention. But we're in this halfway house. We're maintaining a maintenance version of GraalVM for 17 or 21, like an LTS version of GraalVM that would be the equivalent of the LTS version of OpenJDK, is not really happening according to a model that's integrated with the OpenJDK releases. And we're maintaining Mandrel for the community edition for 17, and then for 21, we will drop it eventually in a few months for the 21 version. We'll maintain a 25 version as an LTS version. We hope by then OpenJDK will actually have enough GraalVM in for us to maintain it as part of the standard OpenJDK backports process, LTS maintenance process that we're already contributing to from 8, 11, 17, 21. But we just don't know yet whether it will all be in there. So we may end up having another external maintenance mechanism. And of course, Oracle's GraalVM team are maintaining enterprise editions and legacy editions on the LTS releases, but they have different timescales for the duration of how long they will maintain them for than we do. We want to maintain a 21 version right the way through to 25 and preferably beyond, so that we can get a 25 version out for the next tranche of customers and so on. So this stuff is not really clearly decided. And because the maintenance and the long-term support model is not fully clear, what we're going to call the actual naming isn't that clear either. But I think the thing to worry about is not whether it's what the name is, but how we get this maintenance model in place and how we deal with the fact that at the moment we've got these two projects that aren't really fully merged, and we're maintaining a downstream of the code that isn't fully merged yet.
It's I'm trying to find a way to formulate this. I appreciate that they are trying to simplify, that there's just one thing that's targeting this Java and LTS stuff, which is all good. But this is mainly a marketing exercise, which, is fine. But a thing I think that hasn't been thought through, and it's something we work on, is we have, for example, the Maven artifacts. Like the Mandrel thing that is released is a binary you download, and it's called Mandrel for GraalVM for Java 21 and 17, etc. But for example, the Maven artifacts would have to go back in versioning. So there's these artifact for annotations and other stuff, which is actually what you use in a Quarkus project, or the you can use, and those hasn't been figured out yet. So even though that we are like, what I try to say is like, we're not going to change anything because in time, we are going to align with the version numbers. It's just going to take some time. We'll be in, when it's going to be version 25, because then everything is fine and all is good.
We hope.
So, yeah, we hope. But the thing is, even if we say yes, there will still be traces of the old one, because you otherwise you're gonna go back in versionings and you'll have overlaps and all kind of evil things. And this and we were at Zurich. There was this community meetup with GraalVM and the Oracle team. This came up multiple times. It'd be like, what? Well, it's great you want to have this version alignment, but there's some artifacts going to go back in time. Okay, we just not rename those. Okay, but that does means that you have Maven and Docker images and artifact you download will have different versioning no matter what. And yeah, that's just a consequence.
Can I just add to that, Max? That's one of the benefits of having Mandrel. Mandrel is a product that for our customers, we know will fit with the releases of Quarkus that our customers have, and we will update those and release them with operating system releases and patch updates that will keep that working for customers with a known version of OpenJDK that everything's based on. And that also ties in with the security process as well, where when we do security updates, because we're based on 17 or now 21, we're involved in the security update process for the LTS releases. We know what the security fixes are that need to go into OpenJDK. We're also working with Oracle to deal with security fixes going into GraalVM and Mandrel, so we can make sure that the security story for the Mandrel release is consistent between both the OpenJDK release and the GraalVM release. And that's obviously, critical requirement and critical functional updates. Yeah. That's a requirement.
And just, I want to be very clear that we actually have two versions of Mandrel, right? There's the community Mandrel, which is uploaded and available at github.com/releases and the releases under the GraalVM project. And then there's the Red Hat build of Mandrel, which is part of the Quarkus product. And so those are actually two different ones. But they are same, like they're the same source code. They have the same features. It's just that the prioritized ones is the one that we can, guarantee support for and that kind of thing. And I think that's. I think I want to just highlight again that Oracle announced this donation of GraalVM to the JDK team, which is an ongoing process. But if you go to graalvm.org, so they actually also have a separation. There's Oracle GraalVM and there's GraalVM, the project. And Oracle GraalVM is the thing you get by default when you go to GraalVM, which might surprise people. And that means that version actually has features that are not in the community. For example, like profile guide optimizations and other few other things. All cool, interesting stuff, but it's just the stuff that people have to realize that these are not in the general GraalVM projects.
It also has a license, doesn't it, Max? Do you want to talk about the license?
It has a license too. I'm not sure. Well, I'm not a lawyer. I'll just say the license is supposed to be similar to the Oracle's Java license. So you can use it for free as in no cost, as long as you keep updating, basically. If you stay on a version, then it triggers this thing. I really don't want to make it sound like it's a bad thing. I actually think it's of the licenses Oracle has, I think it's a fairly good one. But it's just something to be that if you want to keep using it and get security updates, you'll have to either at some point you'll have to fall back to paid Oracle or always update. And with Mandrel and the GraalVM community, there's no such requirement, so to speak. We still recommend you should update, but it's not because of the legal stuff. Yeah. We have. Do you want to take the next one here? Question. We haven't actually.
The one about OpenJDK crack or GraalVM native. Yeah.
Yeah. maybe let's save this one.
That's a really good question, Max. I mean, yeah, it's a great thing, but we need to talk
it's a good question
first.
Yes, I'll say let's talk about a few things before, because I'll say this: there's no absolute answer. We'll come up with a good answer, but there's no absolute. It depends on the context. But Andy, maybe you want to give an overview of it. I think. Well, before we go into that stuff, is there anything else in Mandrel you want to cover on? Like, now we talk about why we have Mandrel, mainly for support and just to make sure we can maintain, and something that's focused on native image, and it runs on let's call it clean JDK. Another thing I'm not sure if you mentioned was the fact that remind you, this started like 4 years ago now, I guess 3 or 4 years ago. At the time, at the time there was features in GraalVM. There was Oracle GraalVM that was not in the community one. That we want to make sure that if we had the time and energy, that we could actually contribute or even add if it doesn't show up. Do you want to maybe touch on those, Andrew?
And in fact, it's interesting because Mandrel was something was a place where things that we needed that were missing could maybe have gone in. But in fact, we've actually established a very good working relationship with the GraalVM developers teams, and the things that we were keen to get into GraalVM have been upstream mostly. So the big gap that was missing with GraalVM native was a debugging story and a monitoring tracing story. There was no capability 4 years ago for you to run a binary and know what was going on in that binary as you would by debugging a Java binary, a Java program deployed on OpenJDK. The technology that allows you to debug an OpenJDK just does not work. It cannot work with a system that's been compiled to a self-contained native image. So there was no ability to debug a program. So you could develop your program in OpenJDK, run it through the native image generator, and hopefully it would all just run. But if it didn't, if something was different in the deployed native image from what happened when you ran on the JVM with your Java bytecode, what do? Nothing. There was nothing that you could really do to work out what was going wrong and why it was different. Now, again, when you run on OpenJDK, there's the obvious tool for you to use to understand what the JVM and the JDK and even your application are doing is Java Flight Recorder. There's also all the tracing initiatives like OpenTrace, OTI, and so on for doing instrumentation and monitoring, observability of Java that's going on at a higher level. But in terms of what's actually happening at anything but a very high level, knowing what's actually going on in the Java runtime and the JVM in particular, Flight Recorder is a fantastic tool that gives you enormous amount of information about what happens when your app's deployed, and you can use it to actually find out things about performance, about memory use, also as well as identify things that you just are unexpected, and look for patterns and spot things that are going on that you weren't even aware of, because there's lots of lovely canned analysis tools, and it tells you you're getting all this GC usage. It's because you've got hundreds of these things being hung on to. Do you really want that? All sorts of nice stuff. Nothing again for GraalVM native. It just wasn't there. So we identified these about 4 years ago as key priorities. We had to put support in for some form of debugging, and we had to put support in for JFR to have some sort of monitoring tracing story that would allow people to understand whether apps were not just behaving correctly as they would on OpenJDK, but doing things in a way that was actually performance if it wasn't working out why. So we set off, we offered to the GraalVM team in the Zurich community meeting all those years ago to just give this to them. And they were quite surprised that we would just turn up, produce the code and hand it over. And the last 4 years, we've basically done that. We have a proper debugging story. That's mostly what I've been interested in. And of course, and we also have a JFR story. There's now the ability to get JFR events, including application-defined events, as well as most of the events that occur on the JVM. Not all of them, because some of them don't make sense in a non-dynamic runtime. You don't get class load events. It's all been loaded. Some of them we can't do because we can't just do them yet. Like, we haven't yet got leak detection, although that's being worked on. Because we've not yet got all the full integration into the garbage collectors and the stack management and thread management to do all that, but we will get there. Yeah. So we've got a pretty complete story for JFR and for debugging. Now, the debugging story is probably the weakest one. I say this, and it's all my work, but it's not really my fault. When you build a native image, you take a vast swathes of Java code in jars in the JDK runtime classes, and also the substrate code that provides the Java function, the JVM functionality that on the dynamic VM is implemented in C. Instead, it's implemented in Java. All of that is compiled to a binary image, and the Graal compiler optimizes the hell out of it. So you've got this horrifically complicated, entangled, deeply in-line code that bears a vague relation to the original source code. And there is information at compile time and in the compiler to sort of relate the bits and bytes you get out the back end to the lines of Java you put in at the front end. And what I've done is done what all the compilers that do this sort of thing, a C compiler, a Rust compiler, do. When you take the compiler output and you're building a binary image, all that information that tells you where these bits came from is logged and recorded and dumped into a separate file, a debug info file that tells you how the stack frames are laid out, which registers or which pieces of memory on the stack hold local variables when you're calling a method, which ones hold the arguments, where the static variables are on the heap, what an object looks like, how its fields are laid out, what methods you can call on it. The whole thing is all encoded into the debug info. And you can run a debugger like GDB or the LLVM debugger. And when it looks at this stuff and you stop the code in the middle of some bit of Java somewhere, it knows what's going on, and it gives you stack traces, and it prints objects, and they look like objects. And you can even call methods for certain methods. So there's this very rich information model that allows you to do basic debugging. Obviously, you're debugging heavily optimized code. So when it says you're at this line, you're sort of at that line, because that line might actually exist in 5 different places, and the next instruction might belong to another line that's maybe earlier or later, because these things have all been interwoven to make a really heavily optimized image. And some of the lines of code there isn't machine code for, because that bit got thrown away. But at least it will tell you, it will never tell you that's the source line because it's thrown away, because it knows it was thrown away. So you don't get false positives, but you get some false negatives, in the sense that the opposite of a false positive. You can get situations where you're sort of roughly here, and you have to really understand something about how it's being compiled to debug it. But if you know a reasonable bit about the compiler, you can debug stuff. So if something diverges between what happens on the JVM and what happens when you have a native deployment, there is now a possibility of debugging it. And actually, you don't need to be a complete expert to get benefit out of the debugging, but to really understand a detailed problem where it doesn't behave the same, you need to be quite expert. But it's possible, and that's an enormous step forward.
Yeah,
so that's all my
and that's
yeah. Go on, Max.
Yeah, no, and that's what I was saying, that I believe there was piece of this in the Oracle Enterprise. Like, they had some early debug, and maybe I'm not sure they had it public that they were doing JFR, but like, this was the whole intent for Mandrel, was to have a vehicle where we could have this, because, as you said, we went to Oracle, said, hey, or the Graal VM product, like, this is important for us, because when we started looking at this, when we looked at Quarkus and native image, and said, okay, if you're gonna go out with this, we need some story that we can support for N number of years. And it's something people don't like. I think a Quarkus user doesn't realize that, oh, okay, well, if you use Quarkus to run something and something goes wrong, how do we find out something is there? And of course, a lot of these can be handled by, let's say, you're locking some state. You have your log4j locker, JBoss locker output. You have your open telemetry things. But once you go below, you don't realize that a lot of stuff that the JDK engineers or Red Hat support people do is look at, let's enable JFR, or let's run this JMX call, or something to go deeper.
Mm-hmm.
And we realize, or you guys realize, because I remember you telling me this, because like, that that's just missing. So if you wanted to do something, we needed it, and that's why we push for Mandrel, that to have something that we, in an open source way, could debug. Not that we don't, Oracle can have it's their product, they can do whatever they want, but just like we can. But for us to go and support this, we needed something that was not tied to even Red Hat's ability to productize. It has to be something that
and what was nice was that this was something missing in the community edition. There was debugger in the enterprise edition, although actually it turns out my one's better, and they've used my one now, so that was really nice. They actually, in fact, it was written by a student, and for all he'd done tried and done a good job, it really had lots of problems with it. Nobody had been able to pick this up inside the Graal team, so they've actually adopted my debug capability in the enterprise edition. But that meant we could get it upstream. And that also paved the way for us to get the Java Flight Recorder upstream. Now that also is, again, it fills the gap between all the normal observability stuff and logging, which is very high level, and you can't switch it on and off dynamically. It's all or nothing. It's very heavyweight. Flight Recorder gives you a much more lightweight thing that you can configure and switch on and off. So putting that in also meant that between the very high level overview, heavyweight observability stuff that we had, and this debugging in the middle is an intermediate thing that tells you stuff about what the Java runtime is doing. And in particular, what the substrate VM, what would be normally the OpenJDK JVM is doing, which is stuff that it's not code you can instrument anyway. You can't put logging into the JDK runtime. You can't put logging into OpenJDK. You can enable stuff with the OpenJDK switches, or if you know what you're doing. But it's not the same sort of model. But Flight Recorder is the thing that addresses that, and we now have something that is absolutely compatible with Flight Recorder on the JVM. It works the same way. It uses the same events, produces the same output. You can use it with our Cryostat product inside a container that's got a native image running in it, a Quarkus native image, and you can get the stuff streamed out to the outside world, where you can run mission control and see what's going on and do all the queries and analysis that mission control gives you. So we've got a really, really good story inside Graal VM that's been upstreamed into the community edition. It's being used in the enterprise edition, our code as well. So this is another success where critical usability aspects of the product have been plugged by us, and they've been adopted by the Graal team and upstreamed into their enterprise code as well. And it's a real success story, and it's something that we really needed to be able to have this as a product. So it's been a real win-win for us and for Oracle, and we've had a very good working relationship because of that.
Yeah, and I want to recognize that, as I said, there was some debug work. It was there in Enterprise, and JFR, they also did some work, but also on Enterprise. But us showing up, and now we collaborate, and it's a good
to be fair, I must give them credit. The JFR work, we've had a brilliant junior programmer, just out of college programmer, Robert Toyanoga, who's been doing this work for us, and he's done things that are just superhuman. But he's had help from the Graal team as well; they've contributed. But I don't want to undermine his contribution. It's been absolutely stunning. He's done some amazing work. But it's been a real team effort, and that's really nice as well. That we've got a good working relationship.
And the fun thing with a debugger, I remember when you showed me the first time, I'm like, hey, great, I can do debugging. But as you said, when you go looking, you get disappointed because, I can't, the lines doesn't match up. But you realize, as I said, this is actually compiled code, and therefore things get lost. You can't, it's not like a Java debug. You can do some stuff, but not all.
Even if you're not a particularly experienced user, though, you get an idea of what a stack backtrack is, and including inline code, so you know what's being called and roughly where it's being called.
It's definitely usable, and it's good to have it available as in the toolbox of options. But when I see people look at it and go like, this is not the debugger I'm used to, because it's GDB based instead of like JDB based. I just remind people, how often do you debug the hotspot compiler? like the output of that is something that you just kind of trust and live with. That hey, you expect that what goes into Java when it gets compiled just is the right thing. But you, in at least in principle, native image should be as correct as hotspot compiling.
Yeah, and we've no reason to believe it isn't either. I'm not saying, you know,
No,
this is there for the eventuality that something goes wrong. And there's been one or two small things where that has happened, but we don't know of anything and we're not expecting it. It's just you need belt and braces, and that's what we've got.
And that's what I'm saying, and that's what I'm trying to get to, is that the debugger is probably it's there. It's good to know it's there and it's useful for some specific cases. The more general applicable thing is the JFR, which almost anyone can benefit from. So yeah, but let's go into the more the fun ones, because I can see there's two here. Before, what do you want to do? Do you want to do garbage collection or do different native image stuff? I guess garbage collection is the
let's just deal with the garbage collection thing first. So G1 is available in the Enterprise Edition. And when they say G1, for somehow or other, Oracle have managed to get the source code from OpenJDK and build some of it without building in the context of the OpenJDK virtual machine, but build it as though it's connected to their substrate virtual machine that's defined in Java, with a completely different layout for all the information about what classes are loaded and what an object looks like and all this stuff. So I don't know how they've done this, and I don't know how much they've been able to reuse the existing G1 code base, and how much they've had to sort of build scaffolding around it to plug it in. But they have plugged in the same garbage collection algorithm into their Enterprise Edition. Now, we were quite keen to try and do that with Shenandoah, but it's still only an Enterprise Edition capability. And we would really like them to open source the stuff that plugs things in, so we can build the bits underneath that allow Shenandoah to be connected in and run as garbage collector. In the community edition, the garbage collection is relatively weak. There's a very simple garbage collector. It's not bad for many things, but it'd be really nice to have something that's a bit more throughput oriented for large deployments. It's not that critical a problem, because actually most native image deployments tend to be relatively small micro apps, microservices. So as a consequence, they don't have really enormous heaps. Because they don't have really enormous heaps, if you stop everything to try and garbage collect stuff, you don't get any really enormous pause times. So the motivation for having something like G1 and Shenandoah, which is low pause time, isn't actually as big a concern for a lot of native image deployments. And the flip side is that a very simple basic garbage collector actually has quite good throughput. And one of the things that G1 and Shenandoah sacrifice in order to get lower pause times is that they do work all the time, but concurrently with the application. So you need more than one thread to really get the benefit, or you're continually stopping and starting your application to do a little bit of garbage collector work. And so as well as requiring more CPU, because they're stopping and starting and they're doing stuff in the background, and the Java threads have to allow for the fact that garbage collector might be trying to change something, you do a bit more work every time you read a field or write a field of an object, because you've got to allow for the fact something might be in midair while you're doing it. So you lower throughput. So there's a trade-off between whether you want something simple and low pause times, which works really well for a small heap, or something which has, to get low pause times, sacrifice throughput for a large heap, and requires also several cores to do that. I would like for us to be able to provide a community edition capability like G1 or Shenandoah, and to work with the Oracle team to do that. But at the moment, they're keeping that as an Enterprise Edition capability. It's something that sells things for them, and they have this open core model. So we're really just going to have to live with that for now. There's not much we can do until they decide there's benefits of having this in the community.
To be fair, they have offered that if you do some of the work we could do, then this could move. But yeah, unfortunately, we haven't had people to do it. So yeah, it's kind of a waiting game.
It's complicated. It's not just it's not intransigence on their part. There's also the ability to actually make this work. It's a big commitment. It needs a lot of effort from people.
Yeah.
So.
But I think there was I forgot now. I think there is a PR in Mandrel from either Bellsoft or Alibaba on the parallel GC, or is it the Zero GC?
In fact, it's very close to working actually. And we had Christine Flaubert, who worked on Shenandoah, actually looked at it and was pretty keen to get that in, but it hasn't yet completely gone in. Of course, the benefit of the parallel GC is that when you start to garbage collect everything, if you've got several threads, they can all do all the garbage collection at the same time. So your pause times can be divided. If you've got 6 threads, it can be divided by probably about 3, actually, not by about 6, because you never get full parallelism, but you'll get the pause times will go down because there's 6 threads working to get stuff. If you had 2 threads rather than 1, you'd probably get sort of a quarter of your time back. So you never win completely with parallel garbage collection, but you do improve the time at which the collection happens, and therefore you get smaller pause times. So the fact that that's almost there and almost working is a good thing, and that's probably actually for most applications going to be all that's needed. You don't necessarily need something as heavyweight, as much oriented towards large heaps as G1 and Shenandoah are, and ZGC. So I would think that parallel is probably the most likely solution to meet most people's needs.
Yeah, and just to highlight that, I agree with you. For let's say the Quarkus use case or the Microsoft use case, that they're the large heap. You're trying to avoid having large heaps anyway. And if you are doing large heaps, you probably also have longer running things, and then you're, in general, not for all cases, you might more looking at a JVM run, and then but that's the thing. It's
ironic that you've got pressure there to move from OpenJDK to Graal native to start off a small footprint fast startup, but then as your application grows and your heap requirements grow, you move back to OpenJDK. It's weird. It's what it shows is there's actually trade-offs between using OpenJDK and using Graal VM. They have different characteristics, different throughput, different footprint startup, and you always have to think about what's the best deployment vehicle for the type of application I've got, and the scale of application I've got, and the throughput requirements, targets I need to hit, or the memory targets I need to hit.
Yeah, and that's oh, sorry, Holly. Good.
Oh, yeah, I was just going to say, thanks, Max, that sometimes there's the temptation, isn't there, to try and patch those trade-offs by saying, I want something that's got the best of both worlds, so I want Graal VM, but with, G1 and Shenandoah. But probably that's actually not going to be, it's so tempting, but it's not really going to be the best of both worlds in the way that it seems like it would be.
Yeah. There are different sweet spots for different applications as well, of course. So, it might be that's the best world you could be in for if you're doing this particular thing. But even if your application moves and you develop it and you get a new version, you might find you're no longer on that sweet spot. This is the problem with all application development, and that the technology you're on now doesn't stand still, and the requirements of the application and the user base don't stand still. So you're continually balancing trade-offs, and that can actually have quite fundamental implications for the types of technology you're using. It's what makes programming so incredibly hard to get. There isn't a right solution. There's the right one now, and maybe future-proof if you've predicted the world properly.
Which you never do.
Well, and the fun thing is we talk about all these savings now, and then we have the whole large language model AI burning through all the resources, and it's way more costly, but it's very powerful. So, and it's fine to use a lot of money on that. So but it's always about and it's the one thing. You'll also get into that conversation with the crack versus Leyden versus native image. Is I'll make it concrete for Quarkus. Is the people have to remember, you don't need the reason why Quarkus is fast and efficient is not alone because of native image. It's because of the way we architected how we utilize basically the JVM, how avoid loading classes you don't need, initialize things during builds that are runtime. Literally removing work is the most efficient way to make something fast by not doing it. And yeah, always when I talk about Quarkus, I remind people, yes, Quarkus became popular because of native image, and it's definitely native image is a big mover in stuff like serverless applications or command line tools or that kind of thing. Oracle is definitely fighting for Oracle GraalVM to compete with, let's say, the traditional Java spaces. But Quarkus, if you just apply GraalVM to any other normal application, you will still have something that is slowish because of all the frameworks that lies on top. So it's important to have the full package, which is what we're doing here. Like Quarkus is optimizing the traditional Java things, let's call it that, and Mandrel and native image and Graal, of course, is kind of taking the lower level stuff out. But even if you one without the other is kind of, it's just like it's not going to have the same impact in there. So yeah, but maybe we should go into the different approaches.
Yeah, and I think before actually answering that,
stuff, yeah.
Before answering that, we should probably talk a little bit about Leyden and why Leyden occurred, and what Quark is and why that was started, and how that relates to what GraalVM offers. They're all three ways of trying to address what are obvious failings of the JVM or the JDK runtime, which actually Quarkus also addressed, as Max said. One of the problems with the way people were using OpenJDK or Java was that they were using all the dynamic capabilities of the language to do all sorts of work at runtime, wiring up frameworks and doing bytecode weaving, all sorts of really complicated stuff, pulling classes in at runtime and resolving things through reflection, and things that mean you've got a lot of work to do to actually make something happen because you're doing it with boxing gloves on when you use reflection, and you can't compile things through easily to get really heavily optimized code because the reflection boundary says you don't know what's on the other side of this call. So there was all these things that were happening with indirection and dynamic loading and stuff that meant that a lot of work was being done setting up and getting the application running before you actually did any work to run the application. And even once set up, there was a lot of indirections, and it took a lot of work for the compiler to optimize away all this indirect stuff and realize that it can actually directly wire through stuff and call it straight through. So it took a long time to get up to peak performance, and you couldn't get necessarily the same level of peak performance as if you just called this stuff with a direct call in the first place. So one of the things that Quarkus was built to do was to undo all that and to do a lot of that transformation of the code before it was loaded. And actually, that's a similar sort of thing to what GraalVM was trying to do. The ahead of time compilation of model of GraalVM was to say, well, look, we got all this code in an application that could link in and run stuff at runtime and make all sorts of decisions at runtime. What can we actually do to iron out a load of that stuff and do it in advance and start a program running with a whole lot of stuff pre-initialized, pre-computed, and do the minimal amount of work we actually have to do at runtime by having this stuff that we know will come out the same every single time, just be analyzed and understood and done up front. Now, both of these require a lot of analysis and a lot of pre-processing. If you want to go the whole hog of doing everything at build time and having a completely compiled image, you've got two problems. And this is the problems that we saw with GraalVM. You've got to actually take all those places where the linkage is actually indirect, like a service is loaded based on a class name in a file that's in a jar somewhere. Or that something is called reflectively, and you know it's going to be this API class, but you've no idea which of 20 classes might be called. And you don't even know whether some of those classes will be called because it's only at runtime that the thing's decided. So you don't even know what code you might need to compile into the binary ahead of time. So Graal had to have a whole lot of configuration mechanisms to actually make sure that in order to build an image before you actually deploy with everything compiled in, you get everything, the program gets everything they want. And that's a headache for the programmer. And then secondly, if you want to like pre-initialize static fields of classes, you want to actually run the class initializer at build time and then have all the field values there, rather than having to check every time you try and use a class, is it initialized? Okay, do I need to run? I'll run the class initializer now. If you want to take all those checks out and make sure it's all done in advance, well, you've actually got to do an enormous amount of analysis of the code, because some of the stuff you decide to run in the build time environment rather than runtime environment might actually be something that depends upon what's happening at runtime. For example, if you do something based upon what the machine page size is and use the page size of the build time environment, what happens if you deploy in a machine that has a different page size? You've compiled code that assumes you've got a 4K page, only it's a 64K page. And you try to do things on page boundaries, and suddenly you get absolutely, that's not a valid boundary. So there's lots of things in the operating system, in the actual host environment, in the hardware environment. And there's also things in the Java environment that you can't rely on. For example, if you build time initialize a random variable, you get the same random value sequence every time when you run the thing. If you runtime initialize a random, you get a random value. Well, you really want your randoms to be random, otherwise you've got a security problem. So by trying to do things up front, GraalVM had to deal with all these problems. And then on top of that, also, it was using an OpenJDK runtime that assumed everything happened when you start Java. And if you want to take the actual runtime classes and initialize them, they're not built to do things in advance. There's stuff in the OpenJDK runtime that sets up the standard language processing environment for the standard terminal output and input. If you initialize that on an ENUS locale and you try and run it in a Chinese locale, it's not going to work, or vice versa. But you've got to have that initialized in order to build all sorts of other stuff that depends on being able to write messages. So you can't actually initialize that in advance. They had to cheat to make that work as well. So there's all these problems they faced in doing this.
Yeah, I just say it's 100% correct that one of the things that this leads to is you find all kind of bugs in your app, because Java is actually very forgiving to you. But I know when we did the first, I think the first year, we had this report native image that it worked fine in Java, but in GraalVM failed. And when you run in Docker. So it turns out that in pursuit of reducing the size, we have cut out all the random locales, right? So when Docker runs, it has a default. It doesn't also. It also do a detection of what locale are you running, and if you haven't set that up, it becomes random based on what machine you're running on or something. I forgot the details, but basically, end result was that in Java it kind of adjusted and users code worked, even though they made bad assumptions. And when you ran with Quarkus, suddenly things fell apart because we only had, I think, US, so Unicode didn't work.
Yeah.
Then you go, okay, let's just go enable Unicode, but then your app doesn't. I think is it Java 17? This flipped to be default Unicode.
Yes, there was. That's right. There was a flip there with the strings and the default locale. Yeah, and this is basically an artifact of you're taking a language that was built around doing everything at runtime and trying to turn it into a deployment that does everything, that has as much done at build time as possible. Yeah. And the language, you've got to know that the language is the bits you're using and you're building at build time are the subset that's safe to pre-initialize. And that's something the GraalVM has actually done a good job of. But there are places where they've got it wrong and had to fix it. And there's still places where application code faces the same problem, because it doesn't stop just at the JDK boundary, which is what Graal defines. It happens in the application too. So this is an ongoing problem that you face if you try and shift the computation model.
And that's exactly and GraalVM has done a great job. And in the beginning, they forced some build time up front. The default was to build time in it, and then of course that resulted in problems. But it was like, oh, we'll just begin. And then what we did in Quarkus was kind of manage that setup, saying, hey, this framework is okay doing build time in it, this one is not, or parts of it, and we can change it. But this is the tricky part is that because we've had Java for 25 plus years with these assumptions, even though you try and be like a good citizen, even the JDK takes assumptions about runtime, but also uses code does. And you'll see when in the last couple of years, GraalVM has gone from, hey, we should do build time init to do more and more at runtime, which allows them to have faster startup time, at least for the core level, but the actual application gets slower because they move more from the, let's say, the native, pure raw native to let's do runtime. Where in Quarkus, we try and be a bit more, let's call it aggressive and do build time init because we know that if we try and treat users' code as if they were like it'd be 25 years, people will not be aware of the issues until runtime, right? So this is, we've heard the ask for being more like forgiven and do stuff more runtime, but the problem we say like, well, we do that, we'll just keep repeating the same mistake for 25 years. That even the JVM gets faster, the framework code will be slower because it assumes everything. So yeah. Mm-hmm. Anyway, it's again, it's a choice between choice between my brain.
It's all trade-offs.
Trade-offs is the word. Yeah, it's all trade-offs, and
and they're none of them are easy. There's competing trade-offs as well. So that's the situation with there's Quarkus going along similar lines to GraalVM, but using a different approach to it. Crack is another approach. Crack is based upon the ability to freeze a process and dump its state to disk and then restart it, except that it doesn't necessarily quite restart in exactly the same circumstance. They might even restart on different hardware, a different operating system or whatever. You've got to, there's limits to what you can safely do when you freeze a process at some point during execution and then reconstitute it, dehydrate it, and have it just sort of carry on from where it left off. Now, the idea with Crack was you would start a JVM, load an application, start your server so that all your code's loaded, some of it's being compiled, and then stop and freeze it. And then in the instant when you wanted to run a JVM to handle a request, you just restart that thing and it would be restarted hot, everything ready to run. But the problem is all your network sockets, all your files aren't actually available anymore, or you've got to reconnect them. So you can't quite just do a clean restart. There's operating system resources that are needed. And then you've got this same issue that you might have frozen with a particular seed for a random. And so every time you restart this application to handle a service request, like for a Lambda service or something, you've got the same random number, So it turns out that this freeze and restore thing has some of the similar sort of problems, but it's also got the problem that you could leave things dangling between your process and its connection with the operating system that were valid at the point where you stopped the process and froze it and need to be restored. And now one of the things that the Crack project tried to do is to also provide ways, you might find your application actually has some of its state, which is when it's saved is no longer valid because it was talking to a database, it needs to reestablish the database connection or whatever. So as well as dealing with the sort of basic things that the process freeze and restore have to deal with in Linux, there's also dealing with saving and restoring the JVM and then saving and restoring application state cleanly. So there's an attempt to try and do this. One of the problems is there are no clear boundaries for this because you can stop at any point. It's not clear what's in a sort of semi-initialized state, what's in a clearly initialized state, because all you have to do is just freeze stuff. So you've also got to put stuff in where it says, well, we're about to freeze. Can you guys just sort of get yourself ready? So we're all ready to freeze and then we'll freeze. And suddenly the model for this becomes really, really complicated. There's a lot of stuff you need to plug in, a lot of configurability. And Crack sort of went into the doldrums a bit. I mean, Azure have been carrying on with it and trying to get this to work, but it's and also Amazon were interested. And they have an equivalent sort of thing they provide. It's difficult to get this right. It's easy if you freeze very early on during the JVM runtime to stop and restart and have it clean, but then you don't get the benefit of having your application code loaded. method code compiled with optimized compile code rather than just basic code. So the earlier you do it, the less benefit you get. Finding a sweet spot where you can freeze something and restart, but you haven't committed to all sorts of stuff that you have to repair and have to have a complicated repair mechanism for, that's tricky. So Crack's been trying to do a similar sort of thing. It's tricky. It's not clear cut. And then the last thing of all, Holly has to go pick up a kid, but we'll carry on. The last thing of all was what's going on in Leyden. Now, the OpenJDK team, seeing the fast startup, the low footprint you get from build time initialing things, realized that as well as all this issue that was with middleware using dynamic capabilities everywhere without there being a real absolute priority to use it, but just using it because that was the default. There's worse things than just that overuse of dynamic capabilities. With Java, a lot of things get initialized and get done behind the scenes lazily when they need them. But there was no real easy way for programmers to control when things execute and to maybe easily delay execution. There's various mechanisms. For example, if you have a static field in a class, when the class gets initialized, all its static fields get initialized with it. Now, one of the things you can do is you can put a static field into a dependent class and have a method that gets that static field, which indirectly accesses the dependent class's field. If you initialize the main class, all its static fields get initialized, but the dependent static field won't get initialized until you call something that accesses the dependent class's static field. This is called the lazy static field initialization holder model. It's the technical term. Basically, you put something in a separate class, it can be initialized independent from all the other static variables, because it's only when you make a method call that tries to access the second class's static field that class gets loaded and initialized. You can delay initialize of some data relative to others. So this is like a time shifting mechanism that allows you to make the second class initialize on demand, but it actually also allows you to initialize the first class earlier without incurring the overhead of initializing everything else. You can put a gap between the dependencies, the class loading and class initialization dependencies that you can safely control. It only happens when you call the relevant method that accesses that dependent class. So this is a way of both shifting things forward and shifting things backward. Now, Oracle have thought about this and thought, well, what we could do is we could do a certain amount of pre-computation of state and store pre-initialized state in the actual JDK runtime, in the JMods, the linked Java image. And we could take a basic image, pre-initialize some things if they're decoupled from other classes, and store them, and you commit to having certain things that are pre-initialized, but those other things, because they're independent, because they're lazily dependent on the stuff you've initialized, can be left for initialized later. So they thought of a model of not just build time, but an initial build where you get a JDK and a JVM, and then a transformation on that build where you pre-build certain things and you store them in another JDK JVM image that's had a few things made hard concrete, but still left some things open, and doing that recursively to the point where in the end you might get a fully ahead of time compiled image where everything that can be done at build time is done at build time, and all the code has been compiled. And they're thinking about storing object state and storing compiled code and storing class information about loaded classes in the Java image, along with all the initial stuff that's there in the chat. So this is a way of slowly working towards where Graal is. And it's very much a long-term work in progress. But the nice thing is that some of these transformations, which can, for example, optimize code and pre-compile it, pre-build heap objects that will be the values of static fields, this can be delivered relatively early. We should have this. There's already work being done by Oracle in this area. So it's a different approach. It's trying to do what GraalVM does as a complete one-off step all the way to the end, or Crack has done with a save and restore with a single shot, to do it by stages with transformers that can be built to do little optimizations and can be composed to build a series of optimizations.
Yeah, these are the condensers, right?
Yeah,
that's what they call them.
That's right, yeah. And there's not just the condenser proposal, which is the basic model for how to do this. we've been looking in Red Hat, I've been looking at certain of these one-step optimizations, like could you take constant values? Could you get rid of, for example, a Lambda and replace it with a directly wired class? Because the Lambda classes are created at runtime, but actually you could build the bytecode for those classes at build time and just have a class in your image that meant you didn't have to have the overhead of building your Lambda and hooking it together at runtime. It would just be a direct method call. There's other things, computed constants, where you can have a constant value, but it's a lazily computed constant. But once it's computed, it's constant from there once it gets compiled in. So there's various proposals so far for how to do this time shifting computation and early versus late computation and decoupling the computation.
And then that's and I can imagine people from the outside being like, why are we doing like these like 4 or 5 different approaches, or at least 3?
Well, that was the question. Which one's going to win?
Which one is going to win, right? And it's I think the important thing is to realize that this is good. This is healthy that we're trying out different things, right?
It's a free market of ideas and technologies. And it is good in that regard. Right.
So, but I definitely understand the frustration of like, can't we just pick one of them? And I think the way I see it is that Crack, I think, was at least the one that became most, let's say, like it's been around for a while. Hey, let's treat the VM as like a virtual machine, which is kind of like something we can suspend and resume. But it just never got into the JDK. And for us, from a Quarkus perspective, it never removed the startup time on the first call, right? Like the first call, you had to boot up normally, then take a snapshot, which again was fine when you're treating things as a unicorn in a virtual, like a bare metal machine. But in a container environment, it's actually not easy to do what the Crack is doing. You can work around it, and one way is, for example, Amazon Snapstart, which is not Crack, but it works in a similar manner of, hey, we have a control startup, which is Amazon Lambda, and then before we get any input and traffic, we're going to call the framework using the Crack API, not Crack, but the API, say, hey, take a snapshot or be ready to be suspended. So I know that, so we've done that support in Quarkus, there's Micronaut and Spring and others have done it, but it all requires special coding at runtime. So you need the normal code and then this code to be there. It's kind of like Quark extensions, but just for this specific use case. So is Crack useful? I think it's interesting, and it's for some use cases it is, but I feel like the user experience around it is a bit too tedious for containers. But I definitely, it's available. We have it there. If someone wants to make Quarkus really good for a Crack environment, they can do so. And we will like to receive the PRs for it. But we are focusing more on the startup and native and trying to avoid having this recording statement phase. And this is why native image is interesting, because it starts up and it's it has a consistent startup. Leyden is, as you said, it's like this not middle ground. I wouldn't call it middle ground, but it's like hey, instead of trying to boil the ocean and solve all problems, let's take one piece. And the good thing about that is, over time, once we come to the end of this, it'll be great.
Well, even before that, because it could deliver things incrementally, so we will get better and better.
For sure.
I hope, step by step, which is
and that's what I'm saying. It's better than before, because before I feel like in Java history, we've been stuck on trying to find out what to do because we try to solve all the problems, and now it's like one step, and therefore it's a good thing. But I'm trying to get to is like the question, like which technology is more promising, OpenJDK, Crack, or Graalvm native? I would say both of these are there today. That's their big advantage. The problem with OpenJDK, Crack, and GraalVM native is they don't exist in Java, like the JDK. None of them are in. They are OpenJDK projects, but they are not part of OpenJDK, the Java
mainline release. Yes, yeah,
yeah, right. So in that sense, they are equally good or equally bad. We like GraalVM native mainly because of, well, it works today, and it gives you a binary that is kind of like reliable. Like it behaves the same every time you start. You don't have to deal with it, that kind of stuff. But we are definitely also working with, like, we are, Leyden is definitely where we are spending energy. We're also spending energy in GraalVM native, but Leyden is the one that has the most likelihood of being the most promising, because it's basically being done by the OpenJDK team, and these people picked up. And we hope that the notion we call condensers, GraalVM can fill in the blanks, because as JDK might do, let's say 2 out of 10 steps, GraalVM native can do the others. But even Quarkus, like the stuff that Quarkus does, you could see as a condenser. But I know that's a question up in the air. So to answer the question, if you ask from a Quarkus perspective, it's probably GraalVM native that's more promising, because it's closer aligned with what is coming out of Leyden. OpenJDK crack, I think, is interesting, and I think it's good. It pushes limits. It still works. It worked with it, but yeah, it has some usability issues. That is why we don't spend too much time on it. But hey, you know, a year from now, maybe things change and we found out, hey, that's the way we can solve X, Y, Z, and yeah. So yeah, depends on use case. Trade-offs.
Yeah, that's the other thing, that the rider that always applies to all of these things is, if it fits what you want, well, it's the best thing for you. And the idea there is a best thing is actually, you're already starting to get a slippery slope, because it all depends. These things are about trade-offs and different trade-offs.
Yeah.
But I agree with Max. I mean, the nice thing about GraalVM native, it's quite mature. It's moving towards being part of the OpenJDK project and slowly integrating with it. And OpenJDK is moving towards it. Some of the things that happen in Leyden will mean that things that the GraalVM native runtime has to do now that involve messing around with OpenJDK and potentially getting out of sync with OpenJDK can be done in a way that actually becomes legitimized and guaranteed to be more secure, because OpenJDK is making room for the sorts of things that need to be done in GraalVM to get an ahead of time compilation system to work. The big change that that is used is the mechanism for basically taking some of the JDK classes and rewriting and substituting them with alternative implementations. Now, if you're monkeying around in the internals of the JDK runtime, you could prejudice both the runtime's expectations and the VM's expectations quite dramatically. And so you're doing something that's quite dangerous, and you could introduce semantic changes very easily. And of course, substitutions are also used by application code, and the same story applies there. If we can have a situation where we don't need to do substitutions because the JDK code is built to fit with what GraalVM wants, and we work around the differences and provide compatible mechanisms there, then that risk goes away. And Leyden is one of the things that's moving towards making this tight integration of GraalVM and OpenJDK and the JDK runtime more secure, more reliable, more future-proof. So I think the two together actually have a very strong future, as Max said. But Leyden's a key part of that as well. And of course, Leyden will also provide not necessarily the sort of benefits you want if you're at the GraalVM native end of the spectrum, where footprint and startup are critical, but it will provide benefits for applications that have different requirements to the very dynamic things we saw that people are not tending to use now, and will provide something similar or along the same lines, which is also worth having for different needs. You know?
And the big thing that, well, and this is like in it for the long haul, is that Leyden, the stuff it will do will get more and more people exposed to, hey, do things that are compatible with early, let's say, build time stuff, right? Because that's probably see with the frameworks today. It's like they've been built with assumption, oh, we can delay everything, and therefore everything gets delayed to the end, and therefore everything gets slow.
And Quarkus shows that's a wrong assumption. You look at the benefits Quarkus gives you on the JVM, it's clear that an enormous amount of stuff is much better done at build time. And Quarkus does that.
Yes.
Whether you deploy on the JVM or on GraalVM native, it gives you phenomenal improvements.
Exactly. Yeah. So now, anyway, we've gone over time now, even though we started a bit late. But any other last minute thoughts, Andrew, before we call it quits?
No, I mean, I'm really interested to see where this goes. I think we're in a really interesting position because there's a lot of things going on and things are converging. And I think we will see some really good things coming out of Leyden in the next year or two, and that will really help the GraalVM project. So I'm really positive about this. I mean, I just hope that this all does gel together and we get some real benefits out of it. And so it's usable that users can really understand and use as well. That's the other thing.
Exactly. Make it consumable and
which is the critical, always the most important thing, that this is something that actually is easy to do what you want. This is another thing that Quarkus has concentrated on enormously, usability in Quarkus. You don't even really need to know that you've got GraalVM native underneath there and how it works. You just need to switch it on. Obviously, you need to know what to do if it goes wrong, but you know, Quarkus has made it really easy just to plug native underneath, which is great. And I think that usability story is going to be critical for Leyden as well. These things that will improve the performance have to be something you can plug in.
And that's one of the challenges we have is this is whether we talk with the GraalVM or OpenJDK team or Quarkus is that once you go outside of JDK, you see people doing some weird stuff. And it's actually a challenge that I'll just leave it on this note, is that me and Andrew have been on many email exchanges where I get frustrated that OpenJDK is shutting down things we do, and it's always, sometimes it's like, oh well, you could have done this way. Oh, okay, we'll fix that. But others is like removal unsafe and the modular class path and flags, and in this case with Leyden will be built time in it. It's going to be a balance between doing things so we can make Java faster, but also doing it so we actually can move the rest of the ecosystem with us. And again, it's a bag of compromises.
I mean, one of the things that's going on in OpenJDK is not just Leyden. There's a whole lot of other things being done in OpenJDK. The pace of the project and the stuff that's coming into the project has picked up in the last 5 years enormously. And I think that's the most exciting thing, that if we can do that and have all those extra capabilities that Java's offering, and we can still do something about trading off runtime versus build time computation, or have users do some of their own pre-building things with a condenser model that's appropriate for their application, even if it wouldn't be appropriate for someone else. That's another extension that with all these other things that are in the runtime is really, really amazing. So there's a lot of interesting stuff happening.
We didn't need. I was actually a question. We didn't need. I mean, we shouldn't get. It'll take too long. But one thing that's interesting with native is also how to talk to native. Like there's this whole native image, not native image, sorry, JNI and JNA and what's the this is a JEP for not GMX. What's it called? The improvement to it starts with P. The new proposal for
Panama.
How to do
the foreign memory
Panama,
stuff.
yes,
I mean, there's a really amazing thing that's now coming to fruition.
Once you combine, then the instant comes like, how does native image deal with that? And how does that relate to virtual threads? Because once you have native, as in native binaries, virtual threads doesn't exist, or at least doesn't work the same way. It's fun times. And again, it's going to be a lot of talks about compromises in the future on how this works. So, and Andrew, I think, the whole native integration, I think we should do for another talk. But Andrew, 1,000 thanks for this stuff, and I hope people got the answer. At least we got 2 of them answered to the questions.
Well, and, thanks for inviting me. It was great.
And we'll sign off for today. And